Your database just read one row out of 108 million in 3 disk reads. That's not a cache trick, that's a tree. Run a select with a where clause on an indexed column, and PostgreSQL fires an index scan. No surprise there. But how does it actually find your row? Here's the problem. 100 million rows scattered across gigabytes of disk. A sequential scan would read every single page until it finds the match. That's thousands of disk reads and seconds of wall time. Even worse, if your workload is update heavy, every modified row adds index version churn. One logical row can spawn multiple index entries due to MVCC, bloating pages, and splitting them in a cascading nightmare. And it gets worse. A page split operation moves half the items to a new page, then inserts a downlink in the parent. If the parent is full, it splits too. This is an expensive operation that can lock multiple pages and cascade all the way up. After vacuum runs, you end up with 2 bloated pages instead of 1. So let's take it apart. The structure that turns millions of rows into 3 hops. A B-tree index is a multi-level tree stored across pages. At the very top, one meta page holding metadata. Below that, the root node. Below the root, internal nodes that act as signposts. And at the bottom, leaf pages pointing to your actual table rows. The meta page lives at a fixed position in the first segment file. Query it with the page inspect extension, and you see the magic number 340322, the root block number, and the tree level count. That level 2 means the tree has 3 layers below the meta page: root at level 2, internal nodes at level 1, and leaves at level 0. The root sits at block 290. Every page is 8 kilobytes. Internal pages pack around 600 child pointers. Leaf pages hold around 300 entries. That fan out is everything. Here's the traversal. Start at the root. Binary search finds the key range. Follow the downlink to an internal page. Binary search again. Descend to a leaf. One more binary search, and you've got the heap tuple pointer. Inside each node, Postgres performs a binary search among the stored keys to determine which child pointer to follow. The search key gets compared against node boundaries. This process repeats recursively until you hit a leaf. Inspect a leaf page and you see live items, each with a CTID. That's the tuple identifier, block number, and offset pointing straight into the heap table. In an internal page, the CTID works differently. The block number part becomes a downlink, a pointer to another page in the index itself, one level down. The offset is ignored. Now the magic. 600 to the power of 2 times 300. That's 108 million rows indexed in 3 levels. 2 levels covers 180,000 rows. 3 levels, 108 million. 4 levels, 64 billion. Depth grows logarithmically. Very large tables rarely exceed 4 or 5 levels. And here's the kicker. Over 99% of all pages are leaves. The entire internal tree, root plus all internal nodes, is less than 1% of the index. That means during a lookup, you're only touching the internal pages, the 1%, then jumping straight to the leaf you need. The other 99% sit idle until their specific key range is requested. That's the happy path. Now the honest part, concurrency, bloat, and why even unique indexes lie. B-trees are not MVCC aware. To the index, every table row version is a separate entry. One update to an index column spawns a new index tuple. The old version stays until vacuum cleans it up. High churn workloads pile up duplicates until pages overflow. This is particularly bad when most updates can't use heap-only tuples because an index column gets modified, forcing a new index entry for every index on the table. When a page fills, Postgres splits it. Half the entries move to a new page. A downlink gets inserted into the parent. If the parent is full, it splits too. Splits cascade upward, sometimes all the way to the root. Default fill factor is 90%. That's 10% bloat by design. Under update load, bloat can hit 70% before you notice query slowdown. Postgres reclaims completely empty pages, but makes no effort to consolidate sparse ones. The good news, for single row lookups, index bloat barely matters. Worst case, you read one extra page because the tree is one level deeper than optimal. Since index scans hit internal pages frequently, they're usually cached. 1972, the B-tree data structure is invented. December 1981, Lehman and Yao published the high concurrency algorithm Postgres still uses today. 2008, heap-only tuple updates arrive in version 8.3. 2020, deduplication lands in Postgres 13. 2021, version 14 adds bottom-up deletion to fight page splits before they happen. 2023, the multi-page stats function ships. Deduplication merges duplicate tuples into a single posting list. Instead of 10 identical keys taking 10 slots, you get one key plus a sorted array of tuple IDs. Enabled by default since version 13. Space savings and fewer splits. The deduplication pass triggers periodically when a page is getting full. Postgres scans for groups of duplicate tuples, merges them, and forms a single posting list for each group. The column key values appear only once. Bottom-up deletion is smarter. Before a page split, Postgres scans leaf tuples to find obsolete versions and deletes them in one pass. If enough space opens up, the split is canceled, introduced in version 14. This deletion pass is triggered in reaction to an anticipated version. Churn page, split. Each pass is a bottom-up scan. Start at the leaf, check the heap for dead tuple versions, delete those index entries, and if the page now has room, abort the split. Lehman and Yao's trick. Add a right link pointer to every page and a high key marking the upper bound. Readers never lock pages. Writers lock at most 3 nodes at a time. Concurrency stays high even under write load. The right link lets a reader who lands on a page mid-split follow the chain to the new sibling without restarting from the root. The high key tells you when you've gone too far. No deadlocks, no read waits. But there's a trade-off. Sequential inserts, think timestamps, or auto-increment IDs always land on the rightmost leaf. Every concurrent writer hits the same hot page, low fragmentation, high contention. For time series data, you dodge random page splits because new values go to the right edge. That's nice, but it creates a different problem. Every insert is serialized on one leaf, throttling write throughput under high concurrency. Inspect page, stats across multiple leaves, and you see the pattern. Sibling pointers, chain pages, left to right. Each leaf knows its level. The tree is also a doubly linked list. That linked list structure lets you do efficient range scans. Once you find the first matching leaf, you follow the next pointers without climbing back up the tree. Sequential reads at the leaf level. Page type is marked with a flag. L means leaf, I means internal, R means root. The level field confirms where you are. 0 for leaves, 1 for the first internal layer, 2 for root in a 3-level tree. Quick recap. B-tree indexes use multi-level pages to turn millions of rows into 3 disk reads. Over 99% of pages are leaves. Version churn and page splits cause bloat. Deduplication and bottom-up deletion keep bloat in check. Lehman and Yao's algorithm lets readers run lock-free. And sibling pointers chain pages into a doubly linked list for range scans. 3 disk reads from 108 million rows. That's not magic, it's just math. 600 children per internal page, cubed. If you want more, hit subscribe. Next time we're cracking open the write-ahead log and watching Postgres survive a crash in real time.